Dear students, environmental chemistry is a branch of science which deals with the chemical nature of the environment. It defines the properties, formation, and effects of chemical species present in air, soil, and water. The main focus is to know how contaminants enter the local environment. To study the several issues based on environment, one should have a basic knowledge of chemistry. For a science student, it is important to recognize the importance of change occurring in the environment. In this paper, you will be able to know about the composition of the atmosphere and how the atmosphere protects our Earth. Environmental chemistry includes atmospheric, aquatic, and soil chemistry, and the effect of human activities and biological activities on them. It also discusses the issues of pollution mainly caused by industries. The industrial pollution manipulates the global biogeochemical cycles. In this paper, there shall be detailed study of biogeochemical cycle of carbon, nitrogen, phosphorus, sulfur, and oxygen. In the hydrosphere, we will discuss the issues related to aquatic system of the environment, which includes the hydrological cycle and chemical composition of the water bodies. The aquatic pollution is considered to be the most dangerous issue because water is the necessity of life and therefore cannot be ignored. Environmental chemistry deals with the detailed study of the pollutants which can be organic or inorganic in nature. In this paper, we will discuss the analytical methods for measuring biological oxygen demand, that is BOD, dissolved oxygen, that is DO, chemical oxygen demand, that is COD, and the chlorine demand. Further, we will discuss the composition of soil, macro and micronutrients present in the soil, and pollution caused by fertilizers, pesticides, plastics, and metals. As aquatic and soil pollution is a matter of concern, therefore, purification and treatment of water is considered to be an important part of prevention and control methods. At the end, we shall discuss some major disasters which have happened due to pollution caused by industrial processes and human activities like the Bhopal gas tragedy, Chernobyl, 3 Mile Island, Sivozo, and Minamata disasters. In the first module of environmental chemistry paper, we will focus particularly on atmosphere, its significance and composition. We shall also discuss evolution of the atmosphere as to how the present atmosphere is different from the first, that is primitive, and the second, that is reducing atmosphere, and structure of the atmosphere or how each layer of the environment is different from each other. Let us try to understand it in detail with the help of graphics and visuals.
An atmosphere is a layer of gases surrounding a planet that is held in place by the gravity of the body. An atmosphere is more likely to be retained if the gravity is high and the atmosphere's temperature is low. The atmosphere of the Earth is composed of nitrogen, that is 78%, oxygen, that is 21%, and other gases, which is only 1%. Oxygen used for respiration by humans and animals. On the other hand, carbon dioxide is used by plants and algae for photosynthesis. The Earth's atmosphere consists from the ground up of the troposphere, where the aeroplanes fly in this region of the atmosphere, stratosphere, which includes the ozone layer, mesosphere. This layer protects the Earth from foreign space material like meteors, thermosphere, which contains the ionosphere, and finally, exosphere, satellites orbiting the Earth are found in this region. Each of the layers has a different lapse rate, defining the rate of change in temperature with height. After studying this module, you shall be able to differentiate between air and atmosphere, know about the functions and composition of atmosphere, recognize the layered structure of atmosphere, and understand the importance. Let us begin by asking, what is atmosphere? Earth is the only known planet in the universe with life. Atmosphere is an important part of this life mechanism. It is a thick blanket of air which surrounds the Earth. This atmosphere is due to the gravity of the Earth, which keeps the air and gases attached with the Earth. The density of air in the atmosphere decreases with increasing altitude due to gravity. There is no distinct boundary of atmosphere, only the density of air changes. But we have an imaginary boundary for atmosphere called the Kármán line, which is present in thermosphere. Atmosphere, as we know, is one of the reasons why life exists on Earth. Let us see how this happens. The protection of life from UV radiation and space objects like meteors is done by atmosphere, which is absorbed by some parts of the atmosphere. It helps in plant and animal growth by providing gases like oxygen, nitrogen, carbon dioxide, etc. Atmosphere also keeps the earth warm by retaining the heat of the sun. It helps in radio communication and the movement of aircrafts. This also helps in the treatment of pollutants by spreading the pollutants to a large area and thus reducing their concentration. Atmosphere, as we know, is a thick blanket of air which is composed of many gases. The large proportion of atmosphere is covered by nitrogen, which is followed by oxygen and other gases such as carbon dioxide, carbon monoxide, ozone, water vapor, etc., which form a small fraction of the atmosphere. The atmosphere has not always been the way it is today. It has evolved like everything else. It dates back around 5 billion years ago with the formation of Earth from the solar nebula. Later atmosphere evolved into reducing atmosphere, which dates back to 3.5 billion years ago to 2 billion years ago. Now the present day atmosphere is oxidizing atmosphere that ages around 2 billion years. Categorization of this evolution in different periods is based on the composition of air and all the other activities going around. The formation of planet Earth from the solar nebula saw the creation of the primitive or first atmosphere containing the gases released at the time of formation. The gases were hydrogen, nitrogen, carbon dioxide, carbon monoxide, ammonia, methane, water vapor, and noble gases. This primitive Earth did not have enough gravitational force, and the atmosphere was very hot due to volcanic eruptions. Therefore, most of the noble and light gases escaped away into space.
The atmosphere existed from 3.5 to 2 billion years ago. The hydrosphere formed about 4 billion years ago, resulting in huge oceans from condensed water vapor. During this period, the earth cooled down and differentiation of layers took place into a solid core, liquid mantle, and thin crust. The solid core resulted in a strong gravitational force. The energy Release from accretion of particles and decay of radioactive isotopes caused massive volcanic eruptions. Gases dissolved in the molten magma were reduced while passing through the mantle. Large amounts of nitrogen and carbon dioxide were released into the atmosphere. Most of the carbon dioxide dissolved in water and carbonate sediments built up. Free oxygen was not present. The other gases present were hydrogen, nitrogen, methane, ammonia, and carbon monoxide in trace amounts, hydrogen sulfide, sulfur dioxide, chlorine, etc.
The first forms of life consisted mostly of photosynthetic organisms which released oxygen as a byproduct, but this oxygen was consumed by metals mostly to form oxides, so the atmosphere contained no oxygen at all. Around 2 billion years ago, sea life flourished, and the oxygen produced was more than what was consumed. Due to this oxygen accumulation, plant and animal life began on Earth. All these factors stabilize the atmospheric oxygen to the level that we have today. So the atmosphere became oxidizing. This present day atmosphere is made mostly of nitrogen, oxygen, carbon dioxide, carbon monoxide, ammonia, methane, etc. This atmosphere, as we now know, is divided into five different layers according to the ratio of constituents and temperature variation. These layers are the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. The first layer, that is the troposphere, ranges up to 7 or 18 kilometers, 7 kilometers at the equator and 18 kilometers at the poles. This layer has 75% masses of atmospheric gases. The air near the surface in this layer is higher in temperature than the upper one, meaning the temperature decreases going upwards. This temperature variation gives rise to the turbulence in this layer because the warmer air goes upwards and thus the air blows. Clouds are present in this layer and thus all the weather phenomenon like rain, lightning takes place in the troposphere. The next layer is called the stratosphere. The stratosphere ranges from 7 to 18 to 50 kilometers. The temperature in this place increases with height. This gives rise to the turbulence free environment. Weather balloons and jet aircrafts fly in this region of the atmosphere because the air is very thin and there is very little turbulence. This means that the fuel efficiency of the aircrafts increases. Ozone is an important part of this layer. It acts like a shield and saves the life on Earth from harmful UV radiation. The ozone layer is a thick layer of ozone gas. Ozone, which is a major constituent of photochemical smog, is considered to be a health hazard at the ground level near the surface of the Earth. However, in the stratosphere, the ozone layer absorbs the high energy UV radiation from the sun. This also helps prevent skin cancer and damage to vegetation. The ozone layer is created when the oxygen molecules in the stratosphere absorb UV radiations and dissociate to give atomic oxygen O, which immediately combines with another O2 molecule to form an ozone molecule. This mechanism of blocking UV radiation is based on the absorption of UV radiation by ozone molecule, which leads to the splitting of the molecule into one free oxygen atom and one molecule of ordinary oxygen. Now the free oxygen atom can collide with another ozone molecule to form two molecules of oxygen. Although the absorption of UV radiation leads to the dissociation of ozone molecules, the density of the ozone layer is maintained by the reformation of ozone in the stratosphere. Chlorofluorocarbons, CFCs. and aerosols from volcanic eruptions and meteorite impacts can stay in the stratosphere for prolonged periods of time, resulting in damage to the ozone layer and alteration of global climate. The period of existence of the ozone hole have also seen a considerable increase in the reported incidence of skin cancer when such ozone depleting chemicals reach the stratosphere. The UV light dissociates these chemicals to release chlorine atoms. The released chlorine atoms act as a catalyst and break thousands of ozone molecules. It can react with ozone to form the radical chlorine monoxide. The next layer, the mesosphere, ranges from 50 to 85 kilometers. This layer protects the Earth from foreign space material like meteors. Here too, the temperature decreases with increase in altitude. The place where the layer ends is known as mesopause. This is also the coldest place on the Earth, with temperatures reaching about minus 100 degrees Celsius. It is found that meteors generally burn up in the mesosphere. Thus, this layer protects the surface of the Earth from being pockmarked with craters. The next layer is the thermosphere, which ranges from 85 to 500 or 1000 kilometers. This range varies because of solar activity. When the sun is emitting more high energy radiations, the thermosphere expands under the heat and thus its height at the top changes. The temperature of this layer increases with height because of increased exposure to the sun's radiation. The Kármán line, which is an imaginary boundary of the atmosphere, ends in the same layer at around 100 kilometers from the surface. Most of the UV radiations emitted by the sun are absorbed in the thermosphere. The high energy radiations dissociate the molecules of this layer into atoms, ions, and free electrons. The ions create an electrical layer known as the ionosphere. The atoms and molecules in the thermosphere get excited to higher energy states after collisions with charged particles from space. Transfer of thermal energy takes place during the collisions. The atoms and molecules lose this excess energy as radiations in the visible region of spectrum. These lights are commonly known as the aurora borealis or the northern lights and the aurora australis or southern lights. Lastly, the exosphere is the outermost layer of the atmosphere and ranges from 500 to 1000 kilometers to 10,000 kilometers. This is a part of outer space and consists mainly of hydrogen and helium, and the air is so thin here that it is almost like a vacuum. Generally, the satellites orbiting the Earth are found in this region. The temperature is very high in the exosphere because the particles are directly heated from solar radiation. However, it doesn't appear so high because there are too few particles and so there is not much transfer of energy because intermolecular collisions are limited. This is a part of outer space and consists mainly of hydrogen and helium, and the air is so thin here that it is almost like a vacuum. Generally, the satellites orbiting the Earth are found in this region. Heat budget of Earth's atmosphere. Heat budget of Earth describes the net flow of energy into Earth, which is mainly in the form of shortwave radiation and infrared long-wave radiation. This is because the energy flux is important for understanding the climate change, which also defined as Earth's energy balance. The radiation received by Earth is not uniformly distributed because the equatorial region of the Earth is more heated by sun than the polar regions. Earth's heat engine is the energy absorbed by the atmosphere. This process is coupled with imbalanced solar heating through evaporation, rainfall, winds, and ocean circulation. Stability is attained in the global temperature when the incoming solar energy is balanced by an equal flow of heat to space. The Earth's radioactive equilibrium is distributed in such a way that heat trapping gases rise in concentration, which results in changing the global temperature. The energy absorbed by greenhouse gases is radiated back to space. This is known as the greenhouse effect. This does not occur rapidly due to the inertia of the oceans. This is in continuation until a new equilibrium state is established between the incoming and outgoing radiative forcing. Energy budget. Incoming radiant energy shortwave. The total solar energy received by Earth is measured in watts and denoted as the solar constant. It is estimated that total solar radiation received by the Earth is approximately 340 W/m2, out of which approximately 77 W/m2 is reflected back to space by clouds and the atmosphere. Also, 23 W/m2 is reflected by the surface of the Earth. Hence, only 240 W/m2 of solar energy is left, which is added to the Earth's energy budget. It is estimated that the Earth's geothermal heat flux from the interior of the Earth is about 47 terawatts. This is only 0.087 watt per square meter and represents only 0.027% of Earth's total energy budget at the surface. The minor sources of radiate energy are usually ignored, which includes solar wind, light from distant stars, and thermal radiation. Outgoing radiant energy, long wave. Long wave radiations are those radiations which leave the planet and also known as outgoing infrared energy. The atmosphere of the Earth partially absorbs as cover of cloud can reflect radiation. Generally, transportation of heat energy takes place between the surface layers of the planet to the atmospheric layer by the process of evapotranspiration, latent heat fluxes, and conduction convection process. Ultimately, it results in the transportation of long wave infrared radiation back into space. Earth's energy imbalance. If the outgoing thermal radiation and the incoming energy flux are not equal, unbalancing of energy takes place, and this results in the adding of net heat to the planet. But this is possible only if the incoming flux is larger than the outgoing flux. The absorbed and radiated energy by Earth can be measured indirectly by satellites which are launched into the Earth's orbit. Natural greenhouse effect. The major atmospheric gases, such as oxygen and nitrogen, are transparent to both incoming and outgoing thermal infrared sunlight. On the other hand, water, carbon dioxide, and methane and other trace gases can absorb large thermal infrared energy. 17% of the incoming solar energy is radiated by the surface of the Earth as thermal infrared. However, 12% of it is directly escaping into space. The remaining fraction of incoming solar energy, that is 5 to 6%, is absorbed by molecules of greenhouse gases, which are then radiated by the Earth's surface. The greenhouse gases radiate an increased amount of thermal infrared energy in all directions. This results in the spreading of radiation. They ultimately come back to the Earth's surface. This causes heating of the surface of the Earth even more than the direct solar heating. This is known as natural greenhouse effect. At an altitude of roughly 5 to 6 kilometers, greenhouse gas concentration is too small to freely radiate heat to space. Climate sensitivity and forcings. Basically, change in the incident or radiated portion of the energy from heat budget of the Earth is known as radiative forcing. On the other hand, climate sensitivity is change in the equilibrium temperature due to changes in the energy budget. The Earth's radiative equilibrium is altered by changes occurring in the Earth's climate system. These changes can affect the entering and exiting of energy and hence force temperatures to rise or fall. This is known as climate forcings. Natural climate forcings are changes in the brightness of the sun, variation of the Earth's axis of rotation, and large volcanic eruptions. On the other hand, man made forcings include particles responsible for absorption and reflection of incoming solar radiation, deforestation, responsible for change in reflection and absorption of solar radiation, and increasing concentration of carbon dioxide and other greenhouse gases. This can give either a positive or negative feedback. Positive feedback is the intensifying of original forcing, and negative feedback is the weakening of the original forcing. This can be explained as loss of ice at the poles, which makes the original forcing less reflective, which is an example of positive feedback. The anthropogenic sources of greenhouse gases are responsible for a positive radiative forcing that reduces the net long wave radiation, hence, the radiative equilibrium is disturbed.
Let us recapitulate what we have learned in this module. So, in this module, we have learned how the atmosphere is spread in the outer space about the Earth's surface or envelops it like a thick blanket. The Karman line is considered to be the boundary of Earth, which is about 100 km from its surface. This boundary protects the surface of the Earth as it absorbs the harmful ultraviolet radiation from the sun and help in maintaining the temperature. The atmosphere around the Earth consists of mixture of gases, out of which 78.08% is nitrogen, 20.95% is oxygen, and rest of the fraction is for other gases like argon, water vapor, carbon dioxide, carbon monoxide, etc. We have also learned that the present atmosphere of the Earth is oxidizing in nature, and it is different from the first and second atmosphere in many aspects. Based on temperature variation, the atmosphere is divided into 5 layers, that is, troposphere, stratosphere, mesosphere, thermosphere, and exosphere. All the 5 layers have their own significance in maintaining the temperature on Earth. As per the troposphere is concerned, it is the closest layer to the Earth's surface. Here, temperature decreases with altitude, and most of the weather phenomena takes place in this layer. The second layer we have discussed is stratosphere, in which temperature increases with altitude, and the well-known ozone layer is a part of this layer which protects the Earth from harmful ultraviolet radiations. The third layer we have discussed is mesosphere, in which temperature again decreases with altitude. It is in the middle of the atmosphere. Opposite to it is the fourth layer, that is thermosphere, where temperature increases with altitude. It contains ionosphere, where radio communication takes place. The fifth and the last and the outermost layer of the Earth is exosphere, the temperature of which is very high.